Good evening everyone. Welcome to ACE Engineering College YouTube live session. Myself Dr. M. Prasad, Associate Professor in the Department of Electrical and Electronics Engineering. In this session, I am going to discuss about the previous year university questions based on the transformer, which is come under the basic electrical engineering subject. First question, what is a transformer? So, transformer is a static device which transfers electrical power from one place to another place, one circuit to another circuit with desired change in voltage but without change in frequency. So, see here, this is the definition of the transformer. So, note down this one. Transformer is a static device which transfers an electrical power from one circuit to another circuit with the desired change in voltage and current but without change in the frequency. This is the definition of the transformer. So, this is the circuit diagram, this is the figure of the transformer, this one and this one. For better understanding the concept of transformer, I am using the small animation for better understanding. See here, this is our transformer. So, what is the main function of transformer? It transfers the electrical power from this circuit to this circuit, this area to this area with the desired change in voltage. So, here the primary side of the voltage is 11 kV and this is secondary side of a transformer is 33 kV. So, here voltage changes from 11 kV to 33 kV. At the same time, power is transferred from one place to another place. So, this type of transformers are called the step up transformers. Now, see here, another transformer is there. This is another transformer. The primary side of this transformer is 33 kV and the secondary side is 230 volts, and this 230 volts is directly connected to this house. Okay. Now, here the power is transferred from this side to this side with the change in voltage from 33 kV to 230 volts. So, this type of transformers are called step down transformers. Okay. Now, this is the basic of a transformer. So, basic diagram of the transformer. So, this transformer consists of, this is the primary side, this one is primary side, and this one, this side is called the secondary side. This is secondary side. Secondary side. Okay. Now, the primary side consists of primary applied voltage V1, primary current I1, primary induced EMF E1, primary number of turns N1. Similarly, secondary side of a transformer consists of secondary number of turns N2, secondary induced EMF E2, secondary current I2, and secondary terminal voltage is V2. And this is the flux of a transformer, and this is the core of the transformer. Okay. Now, what is the primary winding of a transformer? This is the primary winding of a transformer. The winding which is connected to the supply is called the primary winding, and secondary winding, this is secondary winding. What is secondary winding? The winding which is connected to the load is called the secondary winding. Okay. Now, we are going to second question. Now, second question is, with the help of the diagram, explain the operating principle of a transformer. transformer works on the principle of mutual induction. See here, transformer works on the principle of mutual induction. So what is mutual induction? When two coils are inductively coupled, if a current in one coil is changed uniformly, EMF get induced in the other coil. So here the current in one coil changed uniformly, then the EMF get induced in the other coil. So I will explain in detail. So see here, when the primary winding is excited by AC voltage, means alternating voltage, it circulates the alternating current. This is alternating current, and this current produces the flux in the core. When this flux links with the secondary winding, according to Faraday's law of electromagnetic induction, the EMF E2 induced in the secondary side of the transformer. This EMF circulates the current in the secondary winding if the load is connected, as shown in the figure. What is the operating principle of transformer? When we are applying a voltage, alternating current circulates in the primary of a transformer, and this current would produce the flux. When this flux link with the primary winding, we will get the induced EMF, primary induced EMF E1, and this flux link with the secondary winding, we will get secondary induced EMF, and this EMF circulates the current when the load is connected to it. Okay. Now next question. So write the relation among the primary voltage, relation among the primary voltage, secondary voltage, and winding turns, or we can say number of turns. Okay. Now we know primary induced EMF of the transformer. We know secondary induced EMF of the transformer. So we know the primary induced EMF. We know primary induced EMF, that is nothing but E1. E1 is equal to 4.44 pi m F N1. This is induced EMF of the transformer, primary induced EMF of the transformer. Now I am considering this one as equation number 1, and the secondary induced EMF is, and the secondary induced EMF is E2. E2 is equal to 4.44 pi m F. This is N2. Now this is equation number 2. Now divide equation number 2 with equation number 1. Dividing equation number 2 with equation number 1. Equation 2 with equation 1, we get E2 by E1, okay, is equal to 4.44 pi m f N2 by 4.44 pi m f, this is N1. Now cancel it, some of the terms get cancelled. See here, this one get cancelled, this one get cancelled. Similarly, this one get cancelled. Or E2 by E1 is equal to N2 by N1, okay, N2 by N1, or E2 by E1 is equal to K, where K is equal to voltage transformation ratio. Voltage transformation ratio, okay. K is equal to N2 by N1. Please note down this relation. These relations are very, very important. Now we are using this relation to solve some of the important problems in later, okay. This is a relation between the primary voltage, secondary voltage, and secondary number of turns and the primary number of turns, okay. We will move for next question. So next question is, explain and draw the phasor diagram of an ideal transformer under no load condition. So a transformer is said to be ideal if it satisfies the following relations and the following properties. The first one, it has no resistance. It has no resistance. Its windings have zero resistance. So first point is, it has no losses, its windings have zero resistance, and third one is, leakage flux is zero. Leakage flux is zero, that is 100% flux would produce in the primary linked with the secondary. Apart from this, the primary applied voltage V1 is equal to the primary induced EMF E1 because there are no voltage drops. Similarly, the secondary terminal voltage is equal to the secondary induced EMF. Therefore, for ideal transformer, ideal transformer, E2 by E1 E2 by E1 E2 by E1 is equal to V2 by V1 is equal to N2 by N1 for ideal transformer. So note down this relation. Note down this relation. We will use this relation for solving important problems. Okay. Now, at a no load on the secondary side, here no load, at a no load on a secondary side of a transformer, the no load current is equal to 0. no load current is equal to 0. Therefore, the primary draws a current, the primary draws a current I1 which is necessary to produce the flux in the core. This current magnetizing the core, that's why this current is also known as magnetizing current. This Im is called the magnetizing current. Im is magnetizing current. So called the magnetizing current. As a transformer is ideal transformer, its windings have zero resistance, it is becoming inductive. So when it is becoming inductive, the magnetizing current, this current, magnetizing current lags the applied voltage V1 by 90 degrees. And this magnetizing current which produces the flux in the core. Therefore, this flux is in phase with this magnetizing current. When this flux link with the primary winding, it will induces the primary induced voltage E1, and when this flux link with the secondary winding, it develops secondary induced EMF E2. According to the Lenz's law, the induced EMF always opposes the cause of producing it, which is nothing but V1. Therefore, the E1, this E1 is antiphase with this V1 with equal magnitude. Similarly, this E2 is antiphase with V1, but its magnitude is not equal to the magnitude of this V1. Its magnitude depends upon the secondary number of turns. These relations are very, very important for drawing the phasor diagram. Okay, remember that one. So this Im lags the V1 by 90 degrees. This Im is in phase with the flux. Okay, this E1 is antiphase with V1 with equal magnitude, and E2 also antiphase with V1, but its magnitude is different. Its magnitude is different from secondary number of turns. Therefore, this E1 and the E2 are in phase with each other. Okay. Now see here, the same things I am writing here. Note down this one. Note down this all points. So as a transformer is ideal, its winding resistance is 0 and it is purely inductive in nature. So when it is inductive in nature, the magnetizing current Im, the magnetizing current, so this magnetizing current Im lags the V1 by 90 degrees. And second, this Im is in phase with the alternating flux. Okay. Now this flux linked with both the windings and producing the induced EMFs E1 and E2 in the primary and secondary. Now according to Lenz's law, the induced EMF always opposes the cause of producing it, in this case which is supply voltage V1, and therefore E1 and E2 are antiphase with V1. Okay, note down these points, these all points. These points are very, very important for drawing the phasor diagram. Now next I am going to draw the phasor diagram. Okay. Now see here, now I am going to draw the phasor diagram. For that, first I am going to take the flux is a constant. So this flux is in phase with, see here, this point, this flux is in phase with magnetizing current. So in phase, this is Im in phase. This magnetizing current lags the supplied voltage with 90 degrees. See this one, magnetizing current Im lags the V1 by 90 degrees. So this is 90 degree means it will come here. This is V1, okay, with 90 degrees. Okay. Now this E1 is antiphase with V1. So V1 is in direction, this direction. So E1 is which direction? This direction, E1. This is E1 with same magnitude. With the same magnitude. This E2 is also antiphase with the V1, but magnitude this depends upon this number of turns. Therefore, this is E2. This is E2. Okay, this is the phasor diagram of an ideal transformer under no load condition. See here, same thing here. The flux is constant. The flux is, I am taking the reference. Im is in phase with this flux. V1, Im lags the V1, means V1 leads the Im with 90 degrees. E1 is opposite to the V1 and both are in phase. Okay. Next question. So, no load current of a transformer is 10 amps. No load current of a transformer is 10 amps at the power factor is 0.25 lagging when connected to a 400 volts 50 hertz supply. Now calculate the magnetizing component of no load current and the iron losses. Now first write the given data. What is given? No load current. So no load current. No load current I0. I0 is 10 amps. And no load power factor is also given. Power factor. This is cos phi naught. How much? 0.25. Okay, now supplied voltage. E1 is equal to how much? 400 volts at a frequency is equal to this is the given data. Now what is our aim? Our aim is to calculate the magnetizing component of no load current. What is magnetizing component of no load current? This is nothing but Im. Magnetizing component of no load current is Im. So what is iron losses? Iron losses are Wi is equal to V1 I0 cos phi naught. Now we are going to calculate this two for the given data. Okay, remember this data. Now the first one is so magnetizing component of no load current. First one is magnetizing. Magnetizing component. Magnetizing component of no load current. This is nothing but Im. Im is equal to I0. This is sin pi naught. Okay. Suppose this is our equation number 1. This is our equation number 1. For the given problem, this I naught is given. For the given problem, this I naught is given. This is given. Now calculate sin pi naught. How to calculate the sin pi naught? Now we know cos pi naught. Cos pi naught is equal to 0.25. Now what is pi naught? Nothing but cos inverse of 0.25. Now use the calculator and tell me what is the value of cos pi naught. So it will come pi naught is equal to 75.522 degrees. Okay. Now we know pi naught. Now calculate sin pi naught. Sin pi naught is equal to sine of and tell me what is the value of sin pi naught. Sin pi naught is equal to, it will come 0.96. Okay, 0.96. Now substitute this sin pi naught and I naught in equation number 1. Now substitute I naught and sin pi naught in equation number 1. Equation number 1. Therefore, Im is equal to, I naught is given how much? I naught. See here, this is I naught is 10 amps. Okay, substitute 10 here and sin pi naught 0.96 and Im is equal to this is 9.6 amps. This is the magnetizing component of no load current. So what is second one? Iron losses. By using this formula we are going to calculate the iron losses. So second one iron losses. Iron losses, we know iron loss Wi is equal to V1 I naught cos pi naught. Substitute all the values, all values are given. See here V1, this is V1 is equal to 400. So Wi is equal to, this is 400. I naught, how much I naught? I naught is 10 into cos pi naught 0.25. What is the value of this one? Use the calculator and tell me what is the value of this one. This will come 1000 watts. Okay, note down this one. Now, the next question. Draw and explain the phasor diagram of a transformer under load condition. Under load condition. Okay. Now, when a transformer is loaded, see here, this is secondary side, this is primary side. So, when the transformer is loaded, the secondary current I2 flowing through the secondary winding as shown in the figure. Secondary current is flowing through the secondary winding when the load is connected. Okay. Now, this flux, this pi is called the main flux. This pi is called the main flux, which is produced by the magnetizing component of no load current. So, see here, this is the main flux which is produced by magnetizing component of no load current. Now, the secondary current which is flowing through the secondary winding set up its own flux. That flux is known as pi 2. Pi 2. So, see its direction, it is moves from right to left, means anti-clockwise direction. This pi 2 is opposes the main flux which is moving from left side to right side. This pi 2 and this main flux both are opposite to each other. As a result, the main flux is decreases. This is main flux, this main flux pi is decreases. When the main flux pi is decreases, the primary induced EMF, this is also decreases. When the primary induced EMF decreases, the vector difference between V1 minus E1 is increases. When the vector difference between these two is increases, the primary draws a more current from the supply. That current is known as I2 dash. This is the load component of the primary current. This current I2 dash just opposite to this I2. Remember this one? This I2 dash is just opposite to the I2. Now, this I2 dash load component of the primary current produces its own flux, that is pi 2 dash, and its direction is a clockwise direction similar to the main flux, and this flux is opposite to the pi 2. See here, see the direction, green color. This pi 2 dash is in this direction and pi 2 is in this direction. So, this pi 2 dash neutralizes the pi 2. As a result, the main flux in the core is constant. Therefore, transformer is also called the constant flux machine. And one more thing, the magnitude and then phase of this I2 secondary current is depends upon the what type of load we are using here. Okay, if this load is inductive, this current lags the E2, and if the load is capacitive, this current leads the E2 or V2. If the load is capacitive, this current I2 is in phase with V2 or E2. So, remember these points. So, these three conditions, when the load is inductive, when the load is capacitive, when the load is resistive, what is relation between this I2 and V2? Because we are using these relations for drawing the phasor diagram later. Okay. Same thing, when the magnitude and the phase of I2 is determined by what type of load we are using. If the load is inductive, we know the secondary current I2 lags the terminal voltage V2, and if the load is capacitive, secondary currents I2 leads the terminal voltage V2. If load is capacitive, both are in phase. Okay. Now, when the transformer is loaded, the primary current I1 has two components. The first one is no load current, this is I naught, no load current I naught. It has two components. The first one is the no magnetizing component of no load current, and the second one is core loss component. This is IC, and second one is load component of primary current. Load component of primary current, that is I2 dash, which is antiphase with I2, antiphase with I2, secondary load current. Okay. So under no load condition, the current under full load condition, the I1 is a vector sum of I naught plus this I2 dash. Okay. I1 is a vector sum of I naught plus I2 dash, no load current and the load component of the primary current. Now we are going to draw the phasor diagram. So case 1, when the load is inductive. See here, this is load is inductive. Okay. Now we know this one, phi m, this is V1. Under no load condition we already studied this one. This is E1, this is E2 or V2, and this is no load current, and this is no load current, and this is IM. Okay, this is IM. So if the load is up to this one, we know, we already studied this one. So when the load is inductive, the current I2 lags the E2. The current I2 lags the E2. It is lagging means it will come somewhere here, this side E2 at an angle phi 2. This is I2. I2 lags the E2 at an angle phi 2. Okay. Now we know this I2 dash, this I2 dash is opposite to this I2. So this is I2 is in this direction. So I2 dash, it will come this direction. This is I2 dash. Okay. We know the resultant of I0 and I2 dash is I1. Resultant of these two is nothing but I1. This is I1. This is I1. This is phi naught, and this one phi 1. Okay. This is the phasor diagram when the load is inductive. Okay. Similarly, I am going to discuss about the case 2 when the load is inductive. Sorry, when the load is same thing. So now the case 2 when the load is capacitive. When the load is capacitive, see here, these things we know. So when the load is capacitive, so this I2 leads this E2, I2 leads E2 by phi 2. Leading means it will come somewhere here, this direction, this side, see here, this is I2 phi 2, and this I2 is opposite to this I2 dash, means it will come somewhere this side. I2 is this one, the I2 dash is just opposite to I2. So see here, this is I2. Now resultant of I0 and I2 dash, resultant of I0 and I2 dash is I1. See, this is I1 at an angle phi 1. This is the phasor diagram when the load is capacitive. Similarly, case 3 when the load is resistive. So see here, this is load is resistive. What will happen? When the load is resistive, this I2 is in phase with this E2. Okay, when the load is resistive, I2 in phase with E2. Okay, so in phase means this I2 is somewhere here. See here, this is I2 in this direction. I2 dash is opposite. I2 is opposite to I2 dash. So I2 dash opposite to this one, it will come somewhere here. Okay, over here. Now resultant of this I0 and I2 dash will come here. See this direction, this is I1. So this is the phasor diagram of a transformer when the load is resistive. Okay, note down. Now the next question. A 50 kVA single phase transformer has 50 number of turns. 50 number of turns on the primary and 200 number of turns on the secondary, and the primary is connected to the 200 volts and 50 hertz supply. Okay, 50 hertz supply. Now determine what is the secondary voltage and maximum value of flux. Now what is secondary voltage? Secondary voltage is nothing but E2 or V2 or E2, or maximum flux means this is pi m. First write the given data. Now solution. Now first given primary number of turns. Primary number of turns, nothing but N1 is equal to how much? 500. Now similarly, secondary number of turns are also given. Secondary number of turns N2. How much? 200 is given. Now the primary is connected to 200 volts, means voltage is also given. Voltage, primary voltage, that is V1, or we can say E1 is equal to how much? 200 volts, and the frequency F is given 50 hertz. Okay. Now our aim is to calculate first secondary voltage. So remember this one, given data. Now the first one is we know the voltage transformation ratio of a transformer. Voltage transformation ratio. Voltage transformation ratio. Voltage transformation ratio, that is E2 by E1 is equal to N2 by N1. Okay, we know this one. Now our aim is to calculate this one. This one is given, this is also given, and this is also given. Now calculate E2. E2 is equal to, now E2 is equal to E1 into N2 by N1. Now substitute these values. What is E1? E1 is given 200. This is 200. What is the value of N2? N2 is 200. N2 is 200 and N1 is 500. N1 is 500 is given. Now cancel this one. How much we will get this? This one, this one, this one, this one. Now E2 is equal to, E2 is equal to 80 volts. E2 is equal to 80 volts. Note down this one. Now what is our second parameter? The maximum flux density. Okay. Now the second one is, we know EMF equation of the transformer. We know E1 is equal to 4.44 pi m F N1. Our aim is to calculate this one. Remaining all E1 is given, and N1 is also given. Calculate pi m. Pi m is equal to, maximum flux is equal to E1 by 4.44 F N1. Substitute these values E1, F and N1. Therefore, pi m is equal to E1. How much E1? E1 is 200 and this is 4.44 into F. F is 50 and N1 is N1. How much N1 is given? This is also 500. This is 500. Okay. Now pi m is equal to 200 by, multiply this one and tell me what is the value of this one. 4.44 into 50 into 500. Use the calculator and tell me. And this will come around this one. Please verify this one. And therefore, pi m is equal to 1.8 milliwaves. Okay. Note down this one. Note down. Now the next problem. A 220 volts, 220 by 440 volts single phase transformer has 1000 number of turns on the primary. 1000 number of turns are given on the primary. primary side, and the maximum flux density. Maximum flux density is a B max. Here B max is given 1.2 waves per meter square. Calculate the number of turns. Calculate number of turns on the secondary, or we can say secondary number of turns, and the area of cross section. Area of the cross section. So now note down the given data. So here solution, primary voltage is given, primary voltage, that is V1, or we can say E1. We are considering the lossless transformer. So this is 220 volts. Okay. Now secondary voltage V2 is equal to 440, and primary number of turns are also given. Primary number of turns, that is N1 is given 1000. Okay, 1000, and maximum flux density. Maximum flux density, that is B max. B max is equal to 1.2 per meter square. Now this is the given data. Now what is our aim? First, calculate the number of turns on the secondary. Number of turns on the secondary means we need to calculate, this is N2, number of turns on the secondary. So we know that, we know voltage transformation ratio, voltage transformation ratio, that is nothing but E2 by E1 is equal to N2 by N1. So in this relation, this E2 is given, E1 is also given, N1 is also given. Our aim is to find out this N2. So what is N2? Or N2 by N1 is equal to E2 by E1, or N2 is equal to N1, N2 is equal to E2 by E1. Substitute all the values. What is the value of N1? N1 is given here, see here, this is N1, 1000 volts, 1000 number of turns, 1000. E2, how much E2 is given? E2 is 440. E2 is 440. E1 is 220. 0. Now this is 2, or N2 is equal to N2 is equal to 2000 number of turns. N2 is 2000 number of turns. Please note down this one. Now second, we are going to calculate the area of cross section. Area of cross section. So we know flux maximum flux is equal to maximum flux density into area. Now area is equal to pi m by B max. Okay, suppose this is our equation number 1. Now calculate this pi m. This is given. This value is given. Okay. Now we know E1 is equal to 4.44 pi m f N1. We know the primary induced EMF of a transformer is E1 is equal to 4.44 pi m f N1. So our aim is to first calculate this one. Therefore, pi m is equal to E1 by 4.44 into F into N1. Okay, now substitute all the values. This pi m is equal to E1. How much E1 is given? E1 is 220 by 4.44 into F50 into N1 is 1000. N1 is 1000 is given. And tell me the answer. Use the calculator and tell me the answer. What is the value of pi m? Pi m is equal to, this is 220, and after multiplying this one, we will get 222,000, and it will come pi m is equal to 0.9 milliviews. Okay. Use the calculator and tell me the answer. This one. Use the calculator. Verify once. Okay. Now substitute this value. In equation number 1. Equation number 1. Now I am going to erase this one. Substitute the value of pi m in equation number 1. We will get area A is equal to, pi m is nothing but 0.9 into 10 to the power minus 3 by how much flux density is given? See here, the flux density is 1.2. This is 1.2. Use the calculator and tell me what is the value of this area of cross section. Area is equal to 8.25 into 10 to the power minus 4 meter square. Verify this one. Note down, note down this one. These relations are very, very important. Please note down this one, this relation and this equation. Okay. Now next question. 300 volts by 50 volts single phase transformer takes a primary current of 3 amps. Primary current is given 3 amps, and neglecting the losses means the primary applied voltage is equal to primary induced voltage, and similarly the secondary terminal voltage V2 is equal to secondary induced EMF E2. Okay. Now determine the full load secondary current. Now here we are going to determine the secondary current. Secondary current means this is I2, we are going to determine I2 and the rating of a transformer. We know rating of a transformer, that is V1, I1, rating of a transformer. So note down, write down the given data, that is voltage, primary voltage how much? V1, or we can say E1 is equal to no losses, that's why. So this is 300 volts. Now similarly secondary voltage, how much? V2 is equal to E2. How much the secondary voltage? This is 50 volts. Okay, neglecting the losses. The primary current is also given. Primary current I1 is also given. How much this I1? I1 is given 3 amps. This is 3 amps. If you want to draw this transformer diagram, you shall draw like this. This is V1, this is V2. Okay, and this is I1. You know, this is I2. Okay. Now we know again, we know E2 by E1 is equal to I1 by I2. Okay, this is given, this one is given, this one is given, and this one is also given. Our aim is to calculate the secondary current which is flowing through the secondary winding of a transformer, this one. Okay, or cross multiply I2 E2 is equal to I1 into E1, this one, or I2 is equal to I1 into E1 by E2. Okay. Now substitute all the values, this I1, E1 and E2. I2 is equal to how much? I1, see, we will verify this one. I1 is this one, 3 amps, this is 3 into E1. E1 is 300 volts and E2 is 50 volts. E1 is 300, this is 300 and this is 50. Now cancel this 0, this is 6. Now 6 into 3, this is 18. I2 is equal to 18 amps. I2 is equal to, this is 18. I2 is equal to 18 amps. Note down this one. I2 is equal to 18 amps. Now second one is the rating of a transformer. Second one is the rating of a transformer. Second one, KVA rating. KVA rating of the transformer. KVA rating of the transformer is V1 I1 into 10 to the power minus 3 kVA. Now substitute the value of V1 and I1. What is V1? V1 is how much? V1 is this one, 300. V1 is 300. I1 how much? The I1 is 3 amps. This is 3 into 10 to the power minus 3 kVA. Okay. Now this will come 0.9 kVA. Okay. Now this is I2 18 amps and the kVA rating of a transformer is 0.9 kVA. Note down this one. Now the next one. Next question is develop the equivalent circuit of a single phase transformer. Now the equivalent circuit of a transformer is the simplified circuit in which impedance, resistance and the leakage reactance of a transformer can be more easily calculated. So note down here the equivalent circuit, the equivalent circuit of a transformer. Equivalent circuit of a transformer is the simplified circuit in which impedance, resistance and leakage reactance of the transformer can be more easily calculated. Note down this one. Equivalent circuit of a transformer. At a no load the no load current, the no load current, no load current I naught, no load current I naught has the two components. No load current I naught has two components. Two components. The first one is Im. It is called the magnetizing component of no load current, and the second one is Ic. This is called core loss component of the no load current. This is called magnetizing component. Magnetizing component of no load current, no load current, and this Ic is core loss component, core loss component. Core loss the magnetizing current is assumed to flow through the X naught, and this core loss component is assumed to flow through the R naught as shown in the figure. So, see, this is the equivalent circuit of a transformer under no load condition. So, no load current has two components, Im which is flowing through the X naught, and Ic core loss component which is flowing through the R naught. This R naught and X naught both are connected in parallel. So, same voltage will be appeared across these two. Therefore, R naught is equal to V1 by Ic, and X naught, this X naught is equal to again V1 by Im. Okay, this is the equivalent circuit of a transformer under no load condition. Now, at full load condition, at a full load, when the transformer is loaded, the current I2, that is secondary current flowing through the secondary winding of a transformer, and due to this secondary current, the primary draws the additional current, that is known as I2 dash, load component of the primary current. See this one, when this load is added, the secondary side I2 current will flowing through. Due to this current, primary draws the additional current, that is I2 dash. This is called no load component. This is called load component. This is called load component. Load component of primary current. Primary current. Therefore, the equivalent circuit of a transformer as shown in the figure. This is the equivalent circuit of a transformer. This is the primary side and this is the secondary side of a transformer. Okay. Now, the equivalent circuit referred to the primary side, means here this is our equivalent circuit of a transformer. All the values of this primary side is transferred to the secondary side, and then under this condition we will draw the equivalent circuit of a transformer. See here, all the values, this value, this one, I2, V2, all will transfer from secondary to primary side. Now the new values and the new equivalent circuit of this under this condition is this one, when secondary is referred to the primary side. So this is new value, E2 dash, R2 dash, X2 dash, V2 dash and I2 dash. Now what is E2 dash? Now this E2 dash is primary equivalent of primary equivalent of secondary induced EMF. Induced EMF. Therefore, E2 is equal to E2 dash is equal to E2 by K, and this one, what is V2 dash? V2 dash is equal to V2 by K, and what is this I2 dash? I2 dash is equal to I into K. Now similarly, what is R2 dash? R2 dash is equal to R2 by this time this is K square. Now what is this X2 dash? Now X2 dash is equal to X2 by K square. These are the new values of the transformer when secondary is transferred to the primary. Now what is this K? What is this K? K is nothing but voltage transformation ratio. What is K? This K is nothing but voltage transformation ratio of the transformer. Voltage transformation ratio. We know voltage transformation ratio is nothing but N2 by N1. N2 by N1. Okay, equivalent circuit of a transformer referred to the primary side. Now the next question. Yes, 6600 by 400 volt single phase transformer has the primary resistance is 2.5 ohms and the secondary resistance is 0.01 ohms. Calculate the equivalent resistance referred to the primary as well as the secondary. And these problems can be solved by considering the two cases. The first case, when this secondary is transferred to the primary, under that condition what is the total resistance on the primary side? See here, the first case, the secondary is transferred to the primary side, what is the total resistance? And the second case, when the primary is transferred to the secondary, what is the total resistance? So we are solving this problem by considering the two cases. Okay. Now first case, when the transformer secondary side is referred to the primary side, means this resistance is come to here. So see here, when this resistance come to here, now this is R2 dash. Now this resistance R1 and R2 dash both are connected in series. So what is equivalent resistance of the series connection? The equivalent resistance, the equivalent resistance is equal to RP, means secondary side, primary side. This is R1 plus R2 dash. Okay, suppose this is our equation number 1. This R1 is given. See here 2.5 ohms. This R1 is given, and this is new value R2 dash when secondary is referred to the primary. Okay, calculate this R2 dash. So calculate this R2 dash. Now this R2 dash is equal to R2 by K square. Now calculate K square. Now K is equal to N2 by N1. Now N2 by N1, N2 how much given? N2 is 400. This is 400 by this is 6600. Okay. Now how much? if this is square and this is also square. So what is the k value? Use the calculator and tell me what is the value of k. K square is equal to, tell me the k square value. K square, you will get k square is 3.67 into 10 to the power minus 3, k value. Now substitute the k value here, substitute this k value here, you will get R2 dash. Now R2 dash is equal to, R2 is given, R2 how much given? R2 0.01 by k square is 3.67 into 10 to the power minus 3, okay, 10 to the power minus 3. Then R2 dash will come, it will come around 2.7 ohms, and tell me the answer. Now substitute this R2 here, R2 dash here, and you will get Rp, total resistance. Rp is equal to, R1 is given 2.5. How much? R2 dash 2.7. This Rp is equal to, it will come 5.2 ohms. Now second case, in the case 2, then primary is referred to the secondary side. Solve this one. Then primary is referred to the secondary side. See here, now these two are connected in series. Now equivalent circuit is equal to, Rs is equal to, how much that is? R2 plus R1 dash, and this value is given, R2 value is given, okay. R2 value is given, calculate R1 dash. Now how to calculate this R1 dash? R1 dash is equal to R1 into k square, okay. Now R1 dash is equal to, R1 is how much? R1 is 2.5, R1 is 2.5, and this k square how much? 3.67 into 10 to the power minus 3, okay. R1 dash, how much? The R1 dash value, tell me the use the calci and tell me what is the value of R1 dash. This R1 dash is equal to 2.5 into 3.67 into 10 to the power how much? Minus 3. How much this is? 9.175 into 10 to the power minus 3 ohms, okay. Now substitute this one here, this one, Rs is equal to R2, how much? R2 is given, R2 is 0.01 plus this value how much? 9 point, this is 9.175 into 10 to the power minus 3. Tell me the answer. Plus 0.01. What is the value? This will come Rs is equal to 0.019175 ohms. Okay, note down this one. Note down this one. Now, derive next question, and the last question is derive the condition for maximum efficiency of a single phase transformer. When a transformer works on a constant voltage and frequency, the efficiency of a transformer is depends upon the load current. When the load current varies, efficiency also varies. Okay, when when a transformer works on a constant voltage and frequency, the efficiency of a transformer efficiency of a transformer varies with load current. If the load current changes, efficiencies also changes. At a certain value of load current, we achieve a maximum efficiency. If a transformer is further loaded, its efficiency start decreasing as shown in the figure. This is the efficiency of a transformer. At particular value of current, we will get the maximum efficiency. If further we are loaded, the efficiency start decreasing as shown in the figure. Now we know the efficiency of a transformer. Now efficiency of a transformer is equal to V2 I2 cos phi 2 by V2 I2 cos phi 2 plus Pi plus I2 whole square and R2. This is the efficiency of the transformer. This is nothing but efficiency. Of the transformer. Now differentiate this efficiency of a transformer with respect to current I2. Differentiate efficiency with respect to I2. Here I am using UV rule. Okay. Now d zeta by di2 is equal to V2 I2 cos pi 2 plus Pi plus I2 whole square R2. Now differentiate this one, d I2 is equal to V2 I2 cos pi 2 minus V2 I2 cos pi 2 d by d I2 is equal this one V2 I2 cos pi 2 plus Pi plus I2 whole square R2. Okay, by V2 I2 cos pi 2 plus Pi plus I2 whole square R2 whole square. Okay, therefore d zeta by d I2 is equal to, now this one d zeta d I2 is equal to V2 I2 cos pi 2 plus Pi plus I2 whole square R2. This is remaining as same. Now differentiate this one. You will get V2 cos pi 2 minus this is same V2 I2 cos pi 2, differentiate this one into V2 cos pi 2 plus this is 0, this is 2 I2 whole square R2 by this whole thing V2 I2 cos pi 2 plus Pi plus I2 whole square R2, this is whole. Okay. Now for maximum efficiency d zeta by d I2 is equal to 0, and therefore note down this term is now become 0, so this is also 0. Okay, now write this one V2 I2 cos pi 2 plus Pi plus I2 whole square R2. Next one is this one V2 cos pi, V2 cos pi 2 minus this term V2 I2 I2 cos pi 2 into V2 cos pi 2 V2 cos pi 2 plus 2 I2 R2 plus 2 I2 R2 is equal to 0. Now multiply this one. V2 I2 cos pi 2 multiply this one into V2 cos pi 2 plus V2 cos pi 2 into Pi. Multiply this one now. V2 cos pi 2 into I2 R2. Okay, this part is over. Now multiply this one, this term, minus V2 I2 cos pi 2, this term, V2 cos pi 2 minus V2 I2, this one and this one, I2 cos pi 2 into 2 I2 So see here, a small correction is there. Here it will come only I2. After differentiation, it will come I2, 2I2. Okay, 2I2. So here this is also 2I2 only. Two I2, this is R2. Now take the, now see here, this term and here V2 I2, this term get cancelled, or V2 cos pi 2 Pi plus V2 cos pi 2 I2 whole square R2 minus V2 I2 cos pi 2 2 I2 and R2. Okay. Now in this is equal to 0. Is equal to 0. Now take the common. This is V2 cos pi 2. V2 cos pi 2, V2 cos pi 2, V2 cos pi 2. Take the common. V2 cos pi 2. Now Pi plus I2 whole square R2 minus I2 into 2 I2 into R2 is equal to 0. Okay, now this term becomes 0. Therefore, or Pi plus I2 whole square R2 minus 2 I2 whole square R2 is equal to 0. Now Pi is equal to I2 whole square R2, and this is nothing but Pi is equal to Pcu. When the copper losses, these are called the iron losses, these are called the copper losses. When the copper losses are equal to iron losses, then only we will get the maximum efficiency of the transformer. The condition of maximum efficiency of the transformer is the copper losses should be equal to the iron losses. Thank you.